All right. So which of these would you say is a scalar? Let's start with magnetic field. Now, let me just give you a clue so that you have an idea what we are doing now. Remember, scalar quantities do not have direction. They only have magnitude. Okay. What the only difference between vector and scalar is that vectors have both magnitude and direction. So, considering what we learned from what we saw in that past question yesterday, with magnetic fields around the magnet, including the magnetic field around an electric a wire conducting electricity. Would you say magnetic fields are scalars or vectors? Hello? No, are you there?
Yes, sir.
Okay.
Um, is a scalar.
So magnetic field. Now, the field itself has direction. Now, let me explain. Do you remember that when I was drawing those lines of the flow of the magnetic field, it had arrows? Did you remember that it had arrows?
Oh, yes, yes, yes.
Yes. So it's actually a vector. So if I'm to group it, this way I will put it. I'll put it under vector. Pressure. Pressure is given by force per unit area. So there is something that I usually say that when a vector is involved in a quantity, right, especially in the formula, most likely that what do you call it? That quantity also has direction. So because pressure is equal to force per unit area, that force has a direction. It's either usually acting downwards on the area that it's acting on, perpendicular to it. So, well, you could say pressure is scalar because when you're calculating, right, we're not talking about a direction. You just know that it is pressure. Okay, so that one could be scalar. Density, where is density? Density is mass per unit volume. That one doesn't have direction at all, so it is scalar. Um, displacement. Displacement is the vector equivalent of distance. So how I usually remember it is that distance can be in any direction. Let me just annotate quickly, but I would yeah. So distance can be from A to B. It can be curvy. A bicycle can be, or a car can drive in a curved manner. But when you want to talk about displacement, this is A and this is B. If you want to talk about displacement is the straight line between A and B. So because displacement is a straight line, that means it has direction. Therefore, it's a vector quantity. So just take note of that. Then let's quickly take on the other ones. Potential difference. Potential difference is current times resistance, I times R. So um, one might say that is not looking at direction at that point. It's just a scalar quantity. Um, that's potential difference. Power is also scalar. Power is the rate at which work is done, or rate at which energy is dissipated. So it's scalar, just a scalar quantity. Velocity is the vector equivalent of speed. Okay, so let's just take note that sometimes some scalar quantities have their vector equivalent. Acceleration is the rate at which the speed of, or is the rate at which the velocity of a body changes, okay, per unit time. So that means that it has direction. It has direction automatically because it's is the rate of change of velocity. Temperature doesn't have direction. It's totally directionless. It's just a scalar quantity. Wavelength for a wave, I think that one has direction, so you can wavelength. Sorry, wavelength is the length of one wave technically. So that's a scalar quantity. Force is a vector quantity. It has direction because of acceleration, of course, not because of mass. Remember, force is equal to mass times acceleration. So force has direction, and that direction is in whatever direction acceleration is in. Frequency of a wave is the number of cycles that wave covers in a second. That doesn't sound like a vector quantity to me. It's a scalar. And then current. Current is the rate, has to do with flow of charges, right? But in itself, it's not a vector quantity either. And the momentum, I think momentum is vector because it's, I'm trying to remember the exact distance for momentum, but momentum has something to do with mass times velocity. Okay, so that's the formula. So because of that, momentum is a vector quantity. But anyways, these are, some things that can give you an idea of what you are dealing with. So that's it. Scalar quantity: speed, distance, age, heat. Strictly magnitude, no directions. Um, um, sorry, let me wipe this thing up that I annotated here. Okay. Okay. All right. So that's it. You just deal with them based on their formula. You can add them, you can multiply them, you can do all sorts of things to them. But vectors have magnitude and direction. So I think we have talked about these three and we agree that they are all what? Vectors. They have direction. Okay. So for because of they have direction, then when you want to add them, when you're doing some calculations with them, you have to also consider the direction. For instance, if a force, imagine displacement. This is an example for displacement. A man walks 54.5 meters east. Take note that east is one direction. So this is not just a man walks for 54.5 meters, period. No, it has a particular direction. So that is displacement. Then they now said, then another 30 meters east again. Calculate his displacement relative to where he started. Well, I mean, it's just easy. Just add them up, right? And then it will definitely be in the east direction because they are going in the same direction. Now let's pretend that, okay, let me see if the next slide has what I want to say. Okay, good. This is a good example. A man walks 54.5 meters east and then 30 meters west in the opposite direction. Calculate his displacement relative to where he started. Guess what? One of them is going to be negative, okay? And in other words, usually the resultant vector will go in the direction of the bigger one, okay? That's what happens in this scenario. And then you can see that the resultant is 24.5. The result of 54.5 minus 30, and it will definitely go in the direction of the bigger one. Okay, and then this is what you do when, well, they're not on a straight line. For instance, the guy moves from, let me see if I can annotate to show what I'm talking about. The guy moves from A to B and then goes from B to C. So you can see the direction is not on a straight line per se, but they have directions at each point. So what does that mean? The displacement will be along this line, okay? So remember, displacement will always have one direction. So somebody may be saying, which one will be the direction? Will it be east or north? No, it can't have two directions. It must have only one. So that's why you can see it looks like it's the hypotenuse of a right angle triangle that we're drawing to get the direction of where the real displacement is. So that's how displacement, vector questions are handled. Okay, so let's see, sorry. Okay, all right, so of course, forces, we know that forces are can be grouped in different ways, but then the most popular way that they can be grouped is into contact versus no contact. So a force is something that when applied will change the motion or shape of an object. It could change the speed, change the direction, or change the shape. Okay, so these are different types of forces. Of course, you can tell that weight acts downwards. I think we said that several times. It acts downwards. Up thrust is upward force exerted on an object that's in a liquid. Sorry. Okay, that's in a liquid or a fluid. That means that could also include gas. Friction, resistive force due to two objects in contact. And then air resistance is a force that uses motion to make an object rise up, okay? And finally, lift, downward force. Oh, hold on. I think I mixed something up. Lift is force that uses motion to make an object rise up. That's what happens in the case of an aeroplane, right? In the case of an aeroplane. Resistive force due to moving through air is air resistance. Sorry, let me make these things. Let me make the arrow point to them correctly. Okay, yes, that's it. All right, so are you with me so far?
Yes, yes.
Okay, now, um, resultant forces, okay? Resultant forces, remember, is as a result of two forces acting in usually either the same direction or in opposite direction. So that's what will lead to what you have, okay? Okay, so this is just a diagram that is just showing you how resultant forces usually happen when they are in in line. Okay, so it's not too different for what we did with displacement back there, where we okay, so I'm trying to see to make sure that we are let me just be sure that this is along the lines of what we saw in that past question. Okay. Okay, so this is an example of weight of something acting on a slope. I think we had one scenario here that was that had to do with a trolley. I think that was this. Yes, that was the question. It had to do with a trolley on a slope. So if you have that scenario, of course, the direction of the force is along the slope of along the slope of the wedge that the trolley is on. So this is an example, a slope that's inclined at 10 degrees to the horizontal, and it says you could use a geometrical method, or I'm not sure now. This is a mathematical method, but yeah. One of them would uh, would fly. So this one does not involve a calculation. Let me see if we have one that involves a calculation. Okay. No, I think there's no one that involves a calculation. All right. We alluded to this, that work done is given by force times distance moved in the direction of the force. Okay, so just remember that work done is force times distance in the direction. It has to be in the force's direction. If it's not in that force's direction, then you can't say that that is work done, let's say. Okay, all right. So these are some vector versus scalar versus vector quantities. So for instance, mass is a scalar quantity. But if you ask somebody what's their mass and they say, usually hear people say what's their weight, but technically in science it's wrong. It's actually mass that the person is telling you in kilograms, but the weight is now when you consider the fact that it's acting downwards. That way, that makes weight a vector quantity. So what that means is that weight will be, remember, force is equal to mass times acceleration. But in this case, weight is a type of force. The only difference now is that it is mass times acceleration due to gravity, which is another name for gravitational field strength. Okay, so that's mg, m times g. Okay. Let's see the next slide. Okay. Okay, so let's see okay, this elasticity, the one that had to do with the spring. And remember, I think this was one of those questions that said, when is a string elastically deformed? Okay, if it's elastically deformed, an object stretch can return to its original length after the forces are removed. If it does this, then we say it has been elastically deformed. If it doesn't do this, then we say it has been inelastically deformed. And that's as a result of probably putting a weight that's too heavy for the spring to carry. So these are, which of these objects are storing elastic potential energy? Okay, so I think a bent metal ruler, does it? I don't think so. Can it bounce back to this thing? I think usually, yes, things that have a spring on them, right, would be able to, what do you call it? Bounce back to their size, original size. So I would go with the C, the one that has springs on a playground ride. Okay. Okay, these are some more details about elasticity, but I'm not going to go into them. Just possibly because this might involve some questions that are above foundation stage. Okay, so let me rearrange some of these pictures so that I don't think, is there anything here? No, nothing. Okay, that's good. Nothing is there. Okay, so remember this formula. Speed is the unit is meters per second, and that's distance, meters divided by second. That's distance over time. Time is in seconds, distance is in meters. Usually you use a straight line graph to depict how speed is for a body that's in motion. Okay. All right. So let's see. Okay, so this is just still emphasizing that velocity is has direction, or talks about direction when it comes to comparison with its scalar equivalent, which is speed. Okay, and you can now tell that speed is velocity is displacement over time. Why? Because it has direction. Remember, the displacement is the vector equivalent of distance. So if you want to talk about velocity in terms of its formula, speed would have been distance over time. So velocity, its vector equivalent, will be what? Displacement per unit time. Now, when you now want to see the rate of change of velocity with time, then you are no more talking about velocity. You are talking about acceleration, because now it is changing per unit time. And that's how a car accelerates or decelerates, because you are no more talking about just distance with respect to time. You're talking about velocity with respect to time. Okay? So whenever you have graphs like this, right, please take note that if you have a graph like this, and it's a graph of velocity against time on the x-axis, the area under the graph is going to give you, sorry, yeah, okay, so the area under the graph is going to give you the acceleration, okay, while the area under the graph for speed, distance, as in speed, distance, and time graph. I think that one just gives you speed. Okay, so this one will give you the acceleration. Okay, so those are just examples of graphs. Okay. Oh, yeah. I almost made, thank God that this slide addresses it. So take a look at this. The area under this graph, right, is the area of that rectangle, the blue rectangle, plus the area of the orange right angle triangle. Can you see that?
Yes.
Okay, so that is actually the distance. So I think yes, I remember now. It's actually the distance, not the acceleration. The acceleration is just the slope or gradient of the downward line. Okay, when for the straight part of the graph, that's the length, not the breadth now. The length, that's the horizontal part of the rectangle. Velocity does not change. So that means it's okay to say that acceleration does not occur. But when acceleration or deceleration occurs, then you now have that line going downwards till velocity becomes 0. Then you can now find that gradient, the gradient of that line, and say that that is acceleration. But the area under the graph is distance. Okay, area under the graph in velocity, a velocity time graph, is distance. Okay, please take note of that, because they may, toss a question like that. Okay, now I'm not sure I came across this, but I'm going to skip it. Terminal velocity. Okay, so there's this formula, v squared equals u squared plus 2s. Anyway, the good thing about most formulas is that they give you guys the formulas in the exam, so there's no problem. You can, it's most likely that you will see the formula given. All right, point of interest, Newton's law. You remember we were talking about this law in one of the questions, right?
Yes.
Okay. So look at it very well. The first law says if the forces are balanced, I think that's what they meant to say there. Are balanced, not balances. Let me delete that and change it to the. If the forces are balanced, there will be no change in motion. So this is honestly, they've changed the statement of some of these laws. I guess it's to help you guys understand them better. But when I remember seeing this first law, this was how it was stated. A body will continue in the state of rest or uniform, that's in a state of motion or uniform motion um, until it is acted on by an external force. Okay, so if for instance a car is still, right, it will stay in, it can stay there as long as you don't apply any force to it. But once you turn on the engine of that car and the engine moves the car in the forward direction or in the backward direction, depending on which gear is engaged, what happens? A force is now comes into the picture. So that is the first law happening. If you want to talk about paraphrasing, you can say that this is a paraphrase of that law. If the forces are balanced, there will be no change in motion. Okay. Now, to further take that, push that example of a car that was stationary. Imagine a car that's in motion. The driver is just coasting along. He's not stepping on the accelerator. He's just driving, right? That car will continue in that state of uniform motion until another force is applied, this time to make it go faster. Okay, so that's why that, I think for me, the way I stated that first law, the way I knew it, says a lot about both when the car is still and when the car is in uniform motion. Okay, so but anyway, if you understand it, that's the important thing, that you understand what's going on and can connect it to your experience in real life. The second law says if the forces are unbalanced, the object's speed and or direction may change. Okay, so that's where you get that force equals mass times acceleration. And of course, the third law says that for every action, there's an equal but opposite reaction, okay, for every single action. Okay. All right. So please take note of those laws. I think I'm sure you remember we saw one question that asked you was targeted at that. Okay. Have you seen this practical before? I want to know. Have you come across this practical before?
No.
Have you come across it before?
Yes, I believe so.
Okay. All right. Did you see it in the mark scheme or just maybe a book?
I think more skill favor.
Okay. All right. Okay, no problem. Let's go to some other concepts for the sake of time. Inertia. Inertia is the tendency of an object to stay in the same state of motion. So this inertia somehow also roughly refers to that thing that I said about an object remaining still until it is acted upon by an external force. An object's internal mass is determined by how hard it is to change its velocity. The more force that is needed, the greater the inertial mass of the object. Okay, so these are just practical things you see in real life. Okay, I don't know why these guys are overlapping, but let me separate them. Okay, looks like we have a lot going on here. Okay, breaking distance, thinking distance. I think we saw a question like this. All right, so now I don't even know which one should be which. But anyway, I'm not sure. I don't know if the one I sent to you arranged it, but let's see if we can help them arrange this thing in the right way. So that guy is riding on a power bike and sees a cat on the road, right in his path. The stopping distance is equal to the thinking distance plus the braking distance. I think that makes sense. The thinking distance for me is the time that he probably saw the cat and is wondering what's the next thing to do. Hit the brakes. And then the braking distance is after hitting the brakes, the distance that the bike would take before it stops, before it comes to a halt. Do you agree with me on that?
Yes.
Okay. So if that's the case, then I think we are good with this formula, right? Stopping distance equals thinking distance plus braking distance. Okay, so remember I told you about momentum being mass times velocity. This is it. This is what it has to do with. Okay, so when talking about momentum, there's just like energy, right? You remember when we're talking about energy, energy is neither created nor destroyed. That is the law of conservation of energy. Also, momentum has conservation, and what it refers to is what? The conservation of momentum. Okay, so you know what? I'm going to skip this. I just saw it referring to higher. Sorry, I'm going to leave this. Sorry, let's move on. I want to believe that collision too is higher. So I'm stepping forward. Okay. All right. So we're on to waves. Take a look at the diagrams. Take a look at the diagrams carefully because they could ask you for you to label them. That's a transverse wave, right? Remember when I told you about transverse waves, that they move in the direction perpendicular, that is at 90 degrees to the direction of vibration. So what that means, I explained it, but let me explain it again. What that means is that, for instance, consider this to be the vibrator, the thing that is causing the wave to move. So I could give you some examples. You throw a stone, a pebble in a pond, and the pond is still, right? So what will happen to that? What will happen to the pond? The direction of vibration is up, down, up, down, up, down. Now, the stone has landed in the water. What do you notice will happen? Ripples will form. Am I right?
Yes.
Why are those ripples forming? If you notice, the ripples start from where the stone hits the pebble hit the pond, and then they spread out, isn't it?
Yes.
So what really happened is that the water molecules are now moving up and down, right? As they're moving up and down, that's the direction of vibration. But guess what direction the waves are moving in? They are moving from the point of impact outwards. They're moving in that direction. They're moving this way. Okay, think about that. They're moving in that direction. But the pebble, the water medium is moving up and down. That's the source of vibration. So if you are asked, what do you think is what kind of wave would be caused by a pebble landing inside water in a pond or in a swimming pool, whatever is the case, that ripple effect is a transverse wave. Okay, just remember that it's a transverse wave. Why? Because of the fact that the direction of vibration is what? Is perpendicular to the direction in which the wave will travel out. Now, let's compare it to, sorry, I wanted to erase, but let me just erase everything at the same time. Let's compare it to sound waves, right? Longitudinal waves. Sound waves are an example of longitudinal waves. I told you yesterday that, do you remember those animations about speakers that look something like this? They show you the speaker like this, and the speaker when the music is loud, right, really loud, that filament, the T, is it? Oh, trying to remember those names. Okay, I can't remember the names, but anyway, you know what I'm talking about. The thing that you see on the speaker that, you know, goes in and out because of this, the volume of the sound is really high. Notice that it is going in and out in this direction, in and out. It's not going up and down. Okay. Now, the air that's in front of the speaker is also traveling outwards like this. That's how they usually draw those symbols for sound, isn't it? Is it not traveling outwards? So because it's the direction of vibration that's producing the sound is also in the same direction that the sound wave is moving out to your ear, or to to the ear that will hear it. Guess what? Sound is a longitudinal wave because both of them are in the same horizontal direction usually. Okay, so what are the parts of a longitudinal wave? You've seen the parts of a transverse wave. The peak, the amplitude is that distance from the x-axis to either the highest or the lowest point in the wave. The peak is on top while the trough is below. Wavelength is the distance. Actually, wavelength can be from here to here. This is how we understand wavelength basically. From here to here, the length of one wave, the exact length of one wave. Now, if you now decide to measure it from the middle of one of them, right, you must also get to the middle of the other one. That's from one peak to another peak is also wavelength. By extension, from one trough, right, to another trough, the distance from one trough to another trough will also be wavelength. Do you understand?
Yes.
Okay, good. All right, so I just felt I should emphasize that because I know we saw questions around this, so I'm very, very sure it's an area where questions will come out, definitely, under foundation. Okay, so let's move on. Okay, this is, oh, okay, nice. Examples include water ripple, that's for transverse wave, and examples, sound waves traveling through air. Okay, so said that. I think we've dwelt on that. So let's move on to something else. Frequency is the number of waves passing a point in each second, okay? And the unit is in hertz. Okay, so that's the unit for frequency. Period is the time it takes for one wave to complete one cycle. And one cycle is the length of one wave. Okay. All right. So are you good with it so far?
Yes.
Okay. Okay, these are other concepts about waves. Remember this formula, V equals frequency times wavelength. That's velocity. Okay. Frequency times the wavelength, that's the velocity. So that's what V is. I think these are practical applications of waves. So look at the picture. What is the wavelength and frequency of the wave? So the frequency, the wavelength is 4 meters. If you look at this picture, how do you think they arrived at 4 meters? Please take a look at the picture carefully. How do you think they arrived at 4 meters?
3 times 4.
3 times 4 or okay, so did you notice how many waves that it looks like we have in this picture? How many the point where the sulfur is? Did you notice that there are about 4 of them?
Yes.
So from the remember we said that wavelength is from the peak of one to the peak of the other. So because there are 4, right, and the distance, the total distance is 12 meters, what they simply did was that, no, sorry, there are 3. There are 3. Let me show you, not 4, please. Sorry, that was a mistake. There are 3. Let's look at them. From here to here. Can you see that?
Yes.
That's 1. From here to here, that's 2. And then from here to here, that's 3. So by the time you divide 12 by 3, that will give you what? 4 meters. Did you get that now?
Yes.
And then the frequency is 3 hertz. That means it covers 3 circles per second. Okay, so that's basically what it's saying. The 3 circles are given by this one that we identified, right? From one, what do you call it? From one peak to another peak, okay? So, okay. All right, so moving on. Do you have any questions so far? Any questions so far?
No.
Okay. Okay. Let me see if there's anything behind this. Okay, this. Okay, so let's just look at the things that are behind here. I think I will restore this to whatever it was before. Light versus sound. Light, of course, is faster than sound, isn't it?
Yes.
Can you tell me one practical instance where that shows up in nature? So why did you, I just wanted to find out, why did you say yes, that light is faster than sound? Why did you say that?
We've done the practical, but I don't remember.
Okay, the practical. Okay, but now let's pretend you don't have the apparatus to do the practical, but you want to prove to somebody that light is actually faster than sound. The easiest way, I noticed my question said from nature, the easiest way to show that light is faster than sound by speed is simply to consider lightning and thunder. Lightning and thunder. Just think about it. When there's a heavy rainfall, I don't know, I guess you guys see rainfall sometimes, right?
Yes.
Okay, but rarely. I guess snow is more prevalent. But then whenever you have rainfall and you have lightning, did you notice that you would always see the lightning before the thunder comes, before you now hear the thunder in the distance? That should tell you that somehow they proceeded from their source at the same time, but you saw the lightning first because light travels faster. Okay, so just keep that handy. Okay, so if you want to remember, how would you easily prove that light travels faster than sound? Lightning versus thunder. Okay, so let's look at how they travel in a vacuum. Is it possible for light to travel in a vacuum? Yes. Just consider sunlight, for instance. The sun is way out in the, I'll not call it outer space, but yeah, somehow it's kind of outer space, right? The sun is in the middle of the solar system, and the earth is just going on its orbit, right? It's said that at the point of outside the earth, the air is very thin or not, oxygen is even lacking. So it's as if there's vacuum there. So light from the sun can travel to us in a vacuum, in spite of the fact that there's no air there. It doesn't need that medium. But guess what? If you remove all the air from a bottle and you have a bell ringing inside, I think that's an experiment, one of those experiments, you will not hear that bell because you took out all the air from it. That's a vacuum, okay? So light doesn't need air to travel as a medium, but sound does, because it basically, the sound usually vibrates the air particles. How is light produced? By luminous objects. That's objects that are source of their own light. Or, yes, basically luminous objects, objects that give out light as sources of light, like the sun, like the moon. Okay, now the moon is really not a luminous object per se, in the sense that it depends on the sun. Okay, so yes, it's still luminous in a way, but it depends mostly on the sun. So how is sound produced? By vibrations. We said that severally today. Light is detected by the eyes, sound is detected by the ears. What next? Can light be reflected? Yes. Can sound be reflected? Yes. Echo. Can light refract? Yes. Can sound refract? Yes. Finally, what is light? Light is a transverse wave, while you already know that sound is a what? Longitudinal wave. Okay. So, are you good with this table? I mean, some of it, you can explain it even without, you understand? You can just explain it like that first one that I gave you, lightning and thunder. You can use that and explain and remember that fact. So, shall we proceed?
Yes.
Okay, so the next one is a practical ripple tank experiment. So I'll leave that for you. You can go through it. I'm hoping that it is not for higher, but for foundation. Okay, so so this is just a diagram that is showing the difference between reflection and refraction and whatnot. Okay, so waves can be absorbed, waves can be transmitted through a medium, and waves can be reflected. Okay, so look at that on the right hand side. Reflection is when the incident wave hits the surface of the medium or the object, like glass. It reflects, bounces off. Some of the light will still pass through, so you can see it if you put your eyes at the other side. And then finally, some of it will be absorbed by the material. Okay, so I would like you to let me know where you got to, so that we can ask a few questions if the need arises. What slide did you get to?
Let me find on my phone.
Okay.
Generating electricity.
What did you say?
Generating electricity.
Generating electricity. Okay. Okay. I don't think we've gotten to that, but okay, that's fine. Okay, so let's continue. I think there was a question on electromagnetic waves being the family of waves, and then the one that asked you to fill up the boxes. So this is under foundation. So take a look at the what do you call it? The spectrum, right? It starts with radio waves, goes on to microwaves. Next is infrared rays, visible light, ultraviolet light, X-rays, and gamma rays. Okay. So I don't know if you can you form an acronym from this? RMI VUX G. Okay, I don't know if you can form. I usually like to remember things like this. I usually like to form acronyms. Okay, so if I'm to form an acronym from this, I could say Ramivox G or Ramivox Gam. I don't know. Ramivox Gam. Okay. Of course, the Ra, I picked that from radio, and the M, of course, the rest, I just picked them, the first letters of each. Ramivox Gam. So just think about it that way. So you'll be able to remember the order in which they show up on the electromagnetic waves spectrum. Okay, so do you have an acronym of your own that you use to remember stuff like this?
No.
Okay, so I'll just encourage you to use that. It's pretty simple. Let me see if I can. Let me see. Sorry. Okay. 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 I was trying to move that thing. All right. So this is what I was saying. Ramivox. Okay. So yeah. Okay, so there we go. Okay, and I said GAM, something like that. Okay, so you can think of that as an acronym that will help you to remember that. Okay, so let's see some uses of electromagnetic waves. So take a close look at this and see if there's anyone that looks is there anyone that looks unfamiliar? Gamma rays used for sterilization, radio waves used for wait a minute. Radio waves. Okay. And I don't want to think that that guy was connected to MRI, but yeah, might just be that. Infrared rays used for remote controls. Ultraviolet rays used in sunbeds. Visible rays, of course, that's the visible part of light, used in photography. X-rays used in airport scanners, and microwaves used for mobile phones. Okay, so are you good with this?
Yes.
Refraction. Okay, so we know that reflection is as a result of bouncing off the surface of a medium. Refraction is as a result of passing through a medium, and the speed of the wave is slowed down. So that's why it looks like a light bends when it goes through glass, thick glass for that matter. Okay, so that's the catch. I didn't really see a lot of questions on refraction, but that's not to say that it can't be asked. But yeah, refraction has two angles that we should take note of. The incident angle, which is the angle between the wave and the normal, and the angle of refraction, which is the angle between the wave inside the medium, which has bent a bit towards the normal, and the normal. Okay, so what are some things to take note of? What are some things to take note of? When a wave crosses a boundary material, it changes its speed through. A wave will bend towards the normal if it slows down, and bend away from the normal when it speeds up through. And the higher the material density, the slower the wave, the light will move. Okay, that makes sense. The heavier it is, that means there are more materials obstructing the movement of the light in that medium. Okay, so, okay, I think we have seen this wave property. Okay, this one is reflection, bouncing off. Okay, an angle of incidence is equal to angle of reflection. Okay. Okay, so these are some other ones, but I'm not too sure whether we should consider them. But let's just consider them for the sake of the fact that they are all related to waves. Diffraction, right? Diffraction. When does diffraction happen? Diffraction occurs when waves pass through a gap or around an object of roughly the same size or smaller than their wavelength. Roughly the same size or smaller than their wavelength. So look at these two diagrams. You can see how diffraction occurs. Okay. All right. So do you remember when we considered magnets?
Pardon? Pardon?
Okay. So take a look at this. Looks familiar?
Yes.
Okay. All right. So these are the diagrams that show attraction and repulsion. Okay. Of course, you can see attraction on the left-hand side is happening between the north and south poles, while repulsion is happening between the north and north poles. And if you look carefully at the diagram where you have repulsion, you can see that the arrowheads are in opposite directions. Why? Because north, lines of magnetic flow will always go from north to south. So imagine if the line coming from one north is facing the line coming from the other north. There will definitely be obstruction. I mean, they will definitely repel each other. But of course, look at what happens on the left-hand side. The line coming out from north is directly going into south. So it's very comfortable. They're moving, they're sort of complementing themselves. So that's why attraction happens. between unlike poles. Okay. So what's the meaning of a permanent magnet? You can see it there. It produces its own magnetic field, and some materials are like that. You can never remove the magnetism from them. But an induced magnet is one which can become a magnet either, okay, when it's placed in a magnetic field, okay, it becomes a magnet. I don't know whether you've seen some of those office pins. When you leave them stuck on a magnet for a long time, after a while, when you take them off, you try and use them to pick another lighter metal, they will attract that lighter metal. Why? They stayed around magnetic material for a long time. Okay. Have you seen that kind of scenario play out before?
Yes.
Okay. So that's just an example of what? Induced magnetism. Induced magnetism. Okay. Take a look at these diagrams. Do they look familiar?
Yes.
You remember yesterday when I was telling you about the rule of the thumb?
Yes, you do the thumb.
That diagram on the right-hand side, you can see the thumb pointing upwards. That shows you the direction of current, while your other fingers there show you the direction of what? The magnetic field that will form around this thing, the wire. Okay. So motor effect. Okay, let's see. Oh, this is higher, sorry. Skipping it. I mentioned that this is the principle on which the fan works, but it's a higher topic, so we're skipping it. Wow. All these guys are higher. Interesting. Okay. Until 1820, excuse me, the only magnetism known was that of permanent iron magnets. Then in 1820, by complete accident, wow. So that means some things, some good things can come out of, can show up as accidents. Some, I say. Hans Christian Ørsted discovered that a current carrying wire produces a magnetic field. He probably wasn't expecting it, but yeah, it happened. So that was a good discovery by Hans. Okay, so electromagnetism. Of course, you can see the word electro. That means electricity is involved, and that electricity is generating magnetism. Okay, so moving on. Okay, now I'm not too sure if solenoids are under foundation or higher, but it seems to me they are under higher, even though they didn't say it here, but I'm just suspecting it. But anyway, look at how solenoids own this thing is. Solenoids field. Now, if you notice something, for the one that had to do with the rule of thumb, did you notice that we don't see north and south playing out here? Take a look at it very well. There's nothing like north or south, yet we know that there's a magnetic field around that wire. Do you see that?
Yes.
But now take a look at solenoids. I don't want to spend too much time on it, but I just want you to take a look at it briefly. Did you see that you have north and south on either side?
Yes.
Now, the big question is this: how do you know where north should be? And how do you know where south should be? And guess what? The answer is very simple. But again, you have to take note of the flow of the direction of the current flow. Now, let me show you what that is. Please, I need you to really pay attention now. See this is the diagram I'm talking about. Maybe I should even make it look like, make it big, because this is all I need to explain what I'm talking about. Let me bring it forward. So yeah, bring to front. Good. Okay. Now, please take a look at this diagram critically. You may not be able to see what I'm saying, so I'm going to annotate, but I want you to just pay attention. Now, in chemistry and in any other science where you see batteries playing out, in those cells, the longer bar, that's the first thing you need to understand. The longer bar that represents, where is my annotator? The longer bar, this guy, this longer bar always represents the positive pole, while the short one always represents the negative pole. So even if they don't show you in the question, remember it. Now, why am I saying that? Why does it make sense to talk about positive versus negative? Because it also determines the direction of flow of current. And that direction of flow of current, just like the other one where it has the rule of thumb, showing you that, okay, if you know the current is flowing upwards, then just put your finger to point to be up in the same direction as the current. The flow of the magnetic field around that wire will follow your remaining 4 fingers. So now let us look at how this one's on is determined. So remember, current will flow from positive pole like this. Just see, I'm annotating with the red ink like this. So you can see it's continuing, yeah, like that, and flowing through these wires, right? Flowing through these wires, flowing through these wires. Now let's imagine it has come to this end. It's still flowing downwards towards what? The negative pole. But that's not where I really want you to see. I want you to look at from the north side. Let's imagine that we were using a camera, right? We're looking at this thing from a camera, and we're looking at it from, we now change the angle of the camera to face the side that where I just drew that arrow. So this will now be the direction of the camera. So this is what you're going to see when you look at the camera from there. Please just bear with me and see if you agree with this. So for the north, right, this is what you're going to see. You see the wire that is showing that the direction of flow is upwards, right? Going like this. Do you agree with that?
Yes.
This is what you will see. Now, I want you to look inside this very well. Because of the, what do you call it? The flow of direction of the current. You can write N like this. I want you to see what I'm going to do now. It's not, I don't know if they did this on the next slide, but let me just do it on this slide because okay. So I think this is it for the North Pole, right? So it flows like this, like this, like this, like this. And I think South Pole is like this. Okay. So this is how you can tell the North Pole and the South Pole. You can see the directions are opposite, right? The North Pole is like this, it's flowing in this direction. So this one will go like this and go downwards. Oh, okay, hold on a minute. Sorry, I think I didn't draw this thing correctly. This is not the direction it will be, please. Sorry for that. Let me wipe this part off. Please, this is the direction. I started wondering why it did not line up. This is the direction. Can you see that?
Yes.
So because of that, can you see that? Can you see that the direction, this arrow like this that I'm annotating on, lines up with this side?
Oh, okay.
Okay, and of course this side also lines up with this side. Now let's come and look at the south side. Let's imagine we put the camera from here. We're now looking at it from this angle, right? This is what we'll see. We'll see it coming out like this. Do you agree with that? We'll see our current flowing out like this.
Yes.
Going downwards. Do you agree with that?
Yes.
Okay. Now look at how S is. The S is. Can you see the arrows are pointing in the same direction as the flow of electricity? This one is pointing downwards. And this one too is pointing downwards. Do you see that? Hello, no, are you there?
Yes.
Okay, all right. So that's it. That's what I basically wanted to show you. But like I said, I'm not going to spend much time on it because I'm not too sure that this is under foundation, so that we don't spend too much time on this. Okay. I think this is one of those practicals, but this is how the electric bell works. That's the principle of the electric bell. A relay. Let's see, electric bell. Okay. Okay. I think these are practicals and applications of magnets in industries. Okay, so you can see where they are using magnets to collect things, heavy things. Okay. Scrap yards and all that. Okay, I'm not too sure. Have we now moved? Have they moved out from? Okay, no. This is like a practical, I think. Okay, so I'm skipping all this now. This looks like it's higher. Okay, motor effect. I think this was under higher. Okay, I'm skipping all this. I'm skipping all this. I'm skipping all this. Okay, but if you really want to study this part, right, I'm sure you can see that this is the left hand. Okay, if you want to study this, it's the left hand that is being used, not the right hand, so that you can easily understand what's going on. Okay. Running out of time. Okay. All right. Okay, so I think this, you said you stopped at generating electricity, right?
Yes.
So have you done this one or you are yet to do it?
I think that's the one that I've stopped at.
Okay, that's the one you were just about to do, right?
Yeah.
Okay. Okay. So I think this generating electricity simply talks about how electricity can be generated from magnetism, right? It simply somehow confirms the fact that just like electricity can produce magnetism, right? If you also set up a magnetic field and move a coil of a wire that doesn't have any electricity, or you move that magnet in a way around that wire, that magnetism can also induce electricity or produce electricity, which can be sufficient enough, depending on how fast that magnet is moved. Okay, so that's basically the principle that the generator works on. Anyway, you guys may not really if you probably didn't come to Nigeria, you may not even have really seen all those generators, the ones that those small ones that you could like pull around, except maybe if you guys are having like a party outside and, well, you may not really have a source of electricity. That's what you would depend on. But yeah, that's basically what that generator works on. Whether it is diesel or petrol powered, the principle is the same. Either you use a Kickstarter or you use your hand to turn it to, set it off. It still involves moving a magnet, or moving, a magnet around a coil in a particular way, to generate electricity to pass through that coil and, of course, to go to the house or whatever it is that you wish to power. Okay, so that's what I was talking about. You can see that coil in between the North and South Pole. So the North and South Pole, just, there's no battery here. Please take note. There's no battery here. But if you turn this setup anti-clockwise or clockwise, electricity will flow through those wires. That's the whole idea. Okay. So remember, in electromagnetism, it's electricity producing magnetism. But now we're talking about the fact that magnetism can also do what? Produce electricity. That's just the basic difference between this topic and the one that came before it. So you would have these principles to catch up with when it comes to generating electricity. Okay, these are some more details, but I don't want to spend too much time on them for the sake that they may be higher topics. Okay. Okay, solenoid things. Okay, so okay. So have you also done transformers?
Yes.
Okay. Okay. All right. So we still have 30 minutes. I don't know if you can quickly source for the 2022 paper 2 physics.
Pardon?
Would you think you can source for 2022 paper 2
Uh,
physics? I think we did. Was it 2023 that we did that yesterday?
I believe so.
Okay. Okay, you sent me something, right?
Yeah.
All right. Let's take a look. Okay. Oh my God. If you have the math scheme, please also send that across.
Yes.
I will but that would just be for me referencing, not like I would use it now. Okay. Let's undo all these annotations. Okay. So let me reshare my screen. Okay. Okay. So this is 2022 physics paper 2 foundation. All right. Okay. So I think some of these questions are questions that you can handle. So let's hear you. What's the answer to this question? What do all electromagnetic waves transfer?
Energy.
Yes, energy, right. That's right. How about this next one? Different types of electromagnetic waves have a different what? Frequency, okay, and a different
Wavelength.
wavelength. Did you say wavelength?
Yes.
Okay, good. Okay. Do you remember the acronym? Rami Vox-GAM, right? So what would A be? Based on our acronym. So remember, Rami Vox, V. So the V stands for what? Do you remember?
Yeah.
Visible.
Pardon?
Visible light. Visible light.
Oh,
The
B.
light you can see. That's the one that's used for photography. That's visible light. Then GAM, the last one is gamma rays. That's B. Okay. It says different types of electromagnetic waves have different uses. Draw one line from each type of electromagnetic wave to its use. Okay, so I think if you remember, microwaves are from phones. So I think they also are from what's that? Microwaves. Microwaves also go from satellite communications, right?
Pardon?
Microwaves are also from satellite communications.
Yes.
Ultraviolet is from let's see. Ultraviolet. Now that's one. I'm not too sure of that one. But I know that X-rays has to do with imaging bones, so that you know, for seeing how the bone structure is. I'm not too sure if ultraviolet energy efficient lamps might be the answer, but I'm not sure. Can you help me confirm from the mark scheme?
Microwaves, satellite communications, ultraviolet,
Okay.
energy efficient lamps,
Okay.
and X-rays, imagining beams.
Imaging bones. Okay, good. Okay. A student investigated how the color of a surface affects the power of the infrared radiation emitted by the surface. And that's what I found. Shiny white surface, matte black surface, electric kettle, measuring cylinder, thermometers, and infrared detector. This one is asking questions about the experiment. Okay, of course, these ones are questions you can answer. It says, what should the student do to reduce the risk of burning herself with hot water? What do you think? What precautions should she take?
Water slowly.
What did you say?
They can pour the water slowly.
Did you say where she should wear a glove or something?
She can pour the water slowly.
Oh, okay, okay. She should pour it slowly. Okay, yeah, yes. Okay, that's one. Okay, okay, no problem. That's a good one. Okay, the next one is asking you about the description of the method. And this one gives you a table. It says, describe the pattern shown by the data in table 1. So can you see any pattern in this data? Can you see any structure to it?
The less time in seconds, the more power in watts.
Okay. So would you say that that's an indication of direct proportionality?
Yes.
Okay. Okay. What is the most likely value for the power of the infrared radiation emitted after 480 seconds? What is the most likely value for the power of the infrared radiation emitted after 480 seconds? So power is okay, let's look at the table. After 480 seconds. Okay. Okay, so now that's the thing. Let's look for the pattern. Time in seconds 0, power in watts 8. When you have 60 seconds, power in watts is 7.2. Okay, so let's see if we can establish that pattern like you said. We suggested direct proportionality. So let's establish that it is direct proportionality. And to establish that it's direct proportionality, I'm going to divide. Did I say the differences? Because it looks like we are adding 60 and something is coming up. Okay, so let's see. 60 divided by 7.2. Let me do that. 60 divided by 7.2 is equal to what? 8.33333. Okay. The next one, 120 divided by 6.5. Sorry. 100, where's my calculator? 180. 180 divided by 6.5 equals, okay. So this is not really, is this really a trend? Okay. I want to see something here. So what's playing out here? 27.69. Do I really see that pattern showing? Okay, so you know what I think? For us to answer this question, right? Can you see? So, oh, okay. Okay, so Noah, I want you to take a look at this thing very well. Did you say as the time increases, power in watts increases too or reduces?
As the time is sorry, yeah, as the time in seconds decreases, the power
Yes.
increases.
No, the power reduces. So take a look at it very well. It started with 8. It now went to 7.2, further reduced to 6.5, and it kept on reducing like that. Can you see that now?
Yes.
So it's a reduction, not an increment. So it's not direct proportionality. It's actually inverse proportionality. It's inverse proportionality. And if I'm to go by what I'm seeing here, sometimes okay, if I can't even say that it's subtraction because 8.0 minus 7.2 is 0.8. 7.2 minus 6.5 is 65 plus 7 is 0.7. 6.5 minus what? Minus 6 will give you 5.9, and 5.9 minus 5 will give you 5.4. So can you see now I have seen a pattern? So you see this thing, you have to just look carefully at it before you can really establish the pattern. Right now, what the pattern I've established is that power in watts is dropping by what do you call it? Is dropping in by different numbers in descending order. Let me explain it again. Please just take a look at it. I don't know if you observed it when I was explaining it. The difference between 8.0 and 7.2 is what? Is 0.8. Are you with me?
Yes.
Okay. The difference between 7.2 and 6.5 is 0.7. Now, I'm now seeing something happening here. The difference between 6.5 and 5.9 is what? 0.6. So it looks like the differences are even reducing by 0.1. The difference between 5.9 and 5.4 is what? 0.5. Can you see the pattern coming out now?
Yes.
The difference between 5.4 and 5.0 is 0.4. The difference between 5.0 and 4.7, I'm expecting it to be 0.3, and it definitely is 0.3. And then finally, the difference between 4.7 and 4.5 is what? 0.2. Now, if I'm to project the next one, right? If I'm to project the next one, what am I going to project? That the difference should be 0.1, which means the next one should be 4.4. That's what will give me 0.1. Am I right?
Yes.
Okay. And that would go for, now let us look at the left-hand side. It's increasing by 60. 60 plus 60 is 120. 120 plus 60 is 180. 180 plus 60 is 240. 240 plus 60 is 300. 300 plus 60 is 360. 360 plus 60 is 420. 420 plus 60 will be what? 480. Are you good with that?
Yes.
Okay. So if that's the case, then we're very, very free to say that for, what do you call it? For 480 seconds, this thing will be what? Power will be what? 4.4 watts. Do you agree with that?
Yes. Yeah.
Okay, so please, oh, you can see how I did this question. I just had to take a good look at the what? The table. Okay, take a good look at it. If they say there's a pattern, then there's actually a pattern. So you just need to see how to look for that pattern. Okay, so moving on. This is an experiment. Sorry, I'm skipping it. Okay, I think this one has to do with gravity and all that. All right. This next one is, you know how Newton discovered that the law, gravity happens. It says an apple hanging from a tree. That's the diagram. It says X marks the center of mass of the apple, also known as center of gravity, CG. Draw an arrow in figure 4 to represent the weight of the apple. Weight always acts downwards. So if I'm to draw an arrow, guess how it's going to look? It's going to be what? It's going to be acting like this, isn't it?
Yes.
Okay. All right. So the next question gives us a formula and tells us what to do with that formula. Calculate the weight of the apple. Remember, weight is mass times acceleration due to gravity or gravitational field strength, which is 9.8 in this case. So do you have your calculator there? Please help us crunch that. Mass 0.150 times 9.8.
1.47.
What did you say?
1.47.
1.47. Okay, so that's going to be what? Newton. Okay. Okay. It says the apple in figure 4 is stationary. Not as much. Why is it stationary? Let's see the options. The resultant force on the apple is downwards. The resultant force on the apple is upwards. The resultant force on the apple is 0. Which one would you say is the answer and why?
0.
Is 0. Why is it so?
Because stationary means it's not moving. So
Okay, yeah, stationary means it's not moving. And at the same time, you remember forces that are equal and opposite. By the time they act on each other, the resultant is 0. Okay, so that's the reason why it's not moving. So still talking about the apple. It says when the apple is ripe, it falls from the tree and accelerates towards the ground, right? It says, why does it accelerate? Because of the gravitational pull, okay? So the resultant force on the apple is what? Now what? Downwards. That's why it's being pulled downwards towards the middle of the earth. So I'll go with option A.
Was that you? Was that you?
Did you get that?
yes.
So the only reason why the apple didn't fall was because it was hanging onto the tree, okay? Resultant force at that point was 0. Okay, the acceleration of the apple is 9.8. Velocity of the apple changes from 0 to 4.9. That means, in other words, the change of velocity is what? 4.9. No big deal there. It now says calculate the time taken for the apple to fall to the ground. And they gave you a formula there. Time taken is equal to change in velocity over acceleration. So can you help us do that? Help us calculate that. 4.9 divided by 9.8. 4.9 divided by 9.8.
0.5.
0.5.
Yes.
Okay, good. Yes, I think it's correct because 98 is half of 49. You're right. Okay. Here's a compass. What do they want us to do with it? It says, why does a compass always point in the same direction when it's not near a magnet? Oh my goodness. It's because the Earth has its own magnetic field. So the north will also point in the direction of the north. That's just the simple reason. So I'll go with the middle answer. The Earth itself has its own magnetic field. Okay. Where are we? It says, what material could the needle of the compass be made from? So remember, magnetic materials magnets will attract magnetic material. So which of these options is a magnetic material?
The Earth.
What did you say? Which one did you say is magnetic?
The Earth.
Aluminium. Did you say aluminium?
No, still.
Steel. Okay. Are you sure about that?
Yeah.
Okay. All right. I'm not too sure about it. I would have equally considered aluminium or copper. Definitely, plastic is totally prohibited from that list as being one of the answers. It's not even possible. Okay. So it says figure 6 shows a current of wire, right? A coil of wire, sorry. And there's a current in that coil. The circles show the position of 4 compasses, all right? Question, which statement describes the magnetic field around the coil? Okay, is it true that the field has the same strength at all points? That cannot be. Now, I can show you that it's not so. Around this area close to the North Pole, it looks like they're more concentrated. Do you agree with me?
Yes.
So there's no way a field can have the same strength at all points. Let's consider the second option. The field is stronger further away from the coil. That's not true because the field should be stronger as you get closer to the coil. That's logical, isn't it? Do you agree with that?
Yes.
Now let's look at the last option. I think that last option is correct. It says the field is strongest at the ends of the coil. I think I'll go with that. The North Pole and the South Pole. I'll go with that. Does this thing agree with that? Does the mark scheme agree with that?
Yes.
Okay, so the last question on that one says, draw one arrow in each circle in figure 6 to show the direction of the magnetic field at that point. So if we were to draw an arrow, this is how it's going to look. Because, what do you call it? Field lines go from the north into the south. The arrow will point in this direction for this one. The arrow will point in this direction for this one. The arrow will point in this direction for this guy. The arrow will point in this direction for this guy. Do you agree with that?
Yes.
Okay. Okay. If two ways the magnetic field around the coil could be made stronger. 2 ways the magnetic field around the coil could be made stronger. Could you consult the scheme for this one?
Bigger magnet.
What did you say?
A bigger magnet.
A bigger magnet. Okay, inside the coil, right?
Yes.
Okay, what else?
Increase the current.
Yes, the current. Yes, that's right. Increase the current. Okay. Okay, you remember that formula for stopping distance? Stopping distance is equal to thinking distance plus braking distance. So the question is this: the stopping distance of a car is the sum of the thinking distance and the braking distance. Which factors affect the thinking distance? Is it the condition of the tires, driving on wet roads, the mass of the car, tiredness of the driver, using a mobile phone? I think I'll go with the last two. What do you think?
Yes. The last two.
Makes sense. This one is just logical. Tiredness of the driver or using a mobile phone, because those are the things that will prevent him from even seeing the obstruction or the obstacle on time and in time enough to hit the brakes. And then braking distance should now start. Explain why a person should not drink alcohol and then drive. What reason would you give?
The person, they become drunk.
Yes, the person might become drunk, and this is all about thinking distance. Okay, so
Increases the reaction time.
yes, the reaction time. Yes, yes, that's right. So, I mean, one with alcohol, the senses are impaired. So, I mean, it's just a no-go area. Okay. Okay, this looks like a graph. It says, what is the speed of the car if the thinking distance is 16 meters? So if I read this off the graph, right, 16 meters will occur between 15 and 16. Between 15 and 17, sorry. So that means the
It's on the
next
other line.
box. What did you say? What's the answer?
On the y-axis.
Yes, on the y-axis. Oh, sorry. I'm sorry. Sorry, on the y-axis. So yes, 16 meters would be somewhere here, right? Can you see my arrow?
Yes.
Okay, so it's somewhere there. So if I trace it to the graph and trace it downwards,
23.
that is 20, 21, 22, 23. Okay, good. That's 23 meters per second. And describe the relationship between speed and thinking distance. How would you describe it? It's proportional, right?
Yes.
Okay. Okay, this is a question that needs calculation. It says a car accelerates at 5.0 at 5.0 what? Meters per second, right? 5.0 meters per second over a distance of 45 meters. The initial velocity of the car is 0. That means it started from rest. Calculate the final velocity of the car. Use the physics equation sheet. Okay, so the formula for this guy is what? Given by V equals, I told you that during our time, there was nothing like physics equation sheet. You have to do it yourself. You have to remember the formula yourself. Okay, so sorry. I don't think this is the one that you need. There are different forms. Okay, let me just write out all the formulas and we'll see which one to use. V equals U plus AT. You can see in this formula, there's no distance included. So it's not the right formula to use. Let's try another one. S equals UT plus half AT squared. Now, the problem with this one is that there is distance according to the question, because distance is given. We cannot use a formula until we have all the parameters that are necessary. So distance is in this one, but the problem now is that there's no time, right? There's no time given. Okay, so let's move on to the last formula, which is what? That V squared equals U squared plus 2AS. And it seems to me that this guy is the winner because I have initial velocity U is there. They told us that it is 0. Initial velocity U. They told us to calculate final velocity, so we don't know it. Just put your V squared there nicely. Okay, so U squared is 0, 0 squared plus what? 2 what? AS. What is the A? The A is the acceleration, which is what? 5. 5.0, which is as good as 5. The S is the distance covered, which is what? 45. Did you see what I just did back there?
Yes.
Okay, now, you know how BODMAS works, right? I'll
Yes.
just multiply. I'll do the multiplications first and then come to the other side. Now, 2 times 5 is 10. 10 times 45 is going to be 450. Are you good? Did you see that? 450. 0 squared is 0, of course. And all this is equal to what? V squared. So that V squared will be equal to what? 450. Okay. Are you good with this?
Yes.
But
Yeah.
now that's not the final answer. The final answer, the question said, find the final velocity of the car. V is the final velocity, not V squared. So you have to take the square root of both sides. So can you help me find the square root of 450 from your calculator to 2 significant figures? What would it be?
Uh, 21.213.
21.213. Okay, so 2 significant figures, right? That looks to me like this. 21. And that is in meter per second. Okay. Are you good with this calculation?
Yes.
Okay. Did you see that? Sorry, I think I left out squared here. Half 80 squared. Did you see that I wrote out the other formulas so that I'll know which one I needed? So when I saw, okay, this is the one that has everything I need, plus one of them should be the ones that you don't know. That's what the question is asking you. That should be one of them. But if you find any equation that there are two things that you don't know, please don't use it. We're not doing simultaneous equation here. Don't use it. Just use the one that you know everything but one, which is what the question is asking you. And if it is not so, you can quickly make the one that you're looking for subject of the formula, and you're good to go. Okay, so I'm going. Let me delete all this, and then I'll. Sorry, let me use my eraser. Makes it faster. Okay. So okay. Oops, sorry. Okay, I'm moving on now. Next question. This is a longitudinal wave. It says, what do the labels A and B represent? Okay, I think we've answered this question before. A is the rarefaction, and while B is wavelength, right?
Yeah. Yes.
The distance between one compression and another compression, that's a wavelength. Okay. Here we go. It says the wave shown in figure 8 has a frequency of 4.0 kilohertz. Calculate the period of the wave. Okay. So how do you calculate period? Remember, frequency is how many cycles are covered in a second. And period, period is the reciprocal of the frequency. That means if I'm to write it down, that means that T is equal to 1 over F. Okay. So 1 over 4 is what? 1 over 4 is 0.25. Okay. So that's going to be 0.25 seconds. I think, yeah. Oh, hold on a minute. Kilo is, sorry, I just found out something I did wrong. Kilo is thousands. So that means is 1 over 4,000, not 1 over 4, please. You know, hertz, the standard unit for hertz is what? Hertz is just hertz, not kilohertz. So if you don't convert it back to hertz before you do this conversion, you'll be in trouble. So that's why it is 1 over 4,000. That's going to be 0, instead of 0.25, because of these 3 zeros, it's going to be 0.00025. Help me confirm this with your calculator. 1 divided by 4,000.
Um, 0.00. Yes, that number.
Is it correct?
Yes.
Okay, excellent. Okay, so that's the answer. So can you see they asked you for the units? These guys are they are pretty smart. They didn't want to give you the units. They want to know whether you understand what key thing about this question. So it's in seconds. That's the unit for period. It's in seconds. Okay, so moving on. Okay. Sound waves are longitudinal. That's a fact. It says figure 9 shows how the speed of sound waves of sound varies with the temperature of air. We've seen this graph before. It's a direct proportionality graph or a straight line graph. But the question is this. Write down the equation that links frequency, wavelength, and wave speed. We know this. We know that formula to be what? V equals F times lambda, isn't it? V equals frequency times wavelength. Okay? Frequency times wavelength. Always remember this. Okay? Does it look familiar?
Yes.
Okay. All right. Of course, they will ask us a practical question now. A sound wave with a frequency of 300 hertz, right, travels through air. The air has a temperature of 28 degrees Celsius. Determine the wavelength of the sound wave. So let's go and take a look at figure 9. Let's take a look at figure 9. Figure 9 from the graph tells us, it said at what? 28 degrees Celsius. So if you look at 28 degrees Celsius, that's the box right before 30. Trace it to the graph, and you will see that it's matched. It goes to 345, 346, 347, 348. That's 348 meters per second. Okay. So now that was what velocity, what we just found now. So 348, what do you call it? 348 is meters per second, is the what? Is the speed. You equate that to frequency is 300 hertz. So 300 times, they say we should find the wavelength. The wavelength is unknown. So just put your lambda there. Of course, anytime something is multiplying what you don't know, simply divide both sides by that thing. So help me use your calculator and do this. 348 divided by 300. What would you get? What would you get?
1.16.
1.16. Okay. And the unit is in meters. Okay. So, yeah. 1.16. Okay. 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 The distance of the London Marathon is 42,000 meters, sorry. Okay. Write down the equation that links distance, force, and work done. Okay. We know that work done is equal to force times distance, right? So that's the formula that links it. The question is this: during the race, competitors work against air resistance. The work done against air resistance by the winner of the race was 3,360,000 joules, right? calculate the average air resistance acting on the winner of the race. The average air resistance. Average air resistance. Average air resistance. Okay. So work done is equal to what? Force times distance. So the air resistance, right, is going to be according to the force that is used to overcome that resistance. Do you agree with that?
Yes.
Okay, so this is going to leave us with just using this formula that W is equal to F times S. F times S. And F times S, so 3,360,000. Okay, so 1,000, 1, 2, 3 equals F. We don't know F. That's technically what we're looking for. The air resistance is in Newton times the number of these S here is not speed, though, is distance. I usually like to use D, but I don't know. Anyway, the formula that told us S. Let me use D to avoid confusion. So D is the distance, and the distance they told us is what? 42,000. You remember? 42,000 meters. So therefore, F will be equal to what? Divide both sides by 42,000. So that's going to be equal to 3,360,000 over 42,000. So, well, yeah, I guess they will let you guys use a calculator. But if you had to do it without a calculator, these guys would simply cancel themselves out, leaving you with 42 and 36. Sorry, 3,360, which 6, I think 6 can do a good job there. 6 in 33 is 5, remainder 3. 6 in 36 is 6, and then you have your 0 there, right? And then you now have 6 in here is 6 in 7 in 42 is 7, plus 6 times 7 is 42. Next, you now have 7 dividing into itself, and 7 into 560 is equal to 80, because 7 times 8 is 56. So the answer is what? 80 Newton. Okay, so are you good with that? Hello? No, are you good with that?
Yes.
Okay. All right. I think we're almost done now. This one says, which equation links distance traveled, speed, and time? We know it. Speed equals distance divided by time. But okay, they don't want to give us that other one. What's the alternative formula? Time. Time. Sorry. Distance will be equal to what? Speed times time. So yes, that's the first one. And of course, there's a question that will help us to apply that. The distance of the London Marathon is 42,000. The winning time for the race was 5,600 seconds. Calculate the average speed of the winner of the race. So speed is distance over time. So can you help us divide that? 42,000 divided by 5,600.
7.5.
7.5. So, and that's meters per second. Okay, okay, this is the last question. It says explain why the speed of a competitor changes during the race. Well, what factors do you think would cause that kind of change? Maybe if the person is applying more effort in movement, isn't it?
Yes, like turning a corner.
To move faster and all that. So those are the things that could make the speed to change during the race. I mean, that's basically what happens when acceleration, occurs. That's what happens. That's what happens. Okay. So I think you can send me this thing, the mark scheme, right? Okay, I think you sent it. Okay. So I think this is your last paper, right?
Yes.
Okay, that's nice. So I'm sure you're looking forward to it. So yeah, it's all good. When do the results for the exams usually come out?
After summer.
After summer.
Yeah.
Okay. Okay, that would be August, about August, right?
Yes.
Okay. Okay. That's interesting. That's a long wait. What would you be doing before that time?
Pardon?
I said that would be quite a wait. Would you? Okay, you guys will still be. You'll still be having a program then, right? Your program will continue, right?
What program?
Yes.
What program?
I mean, your school. That's what I mean.
I'm done.
Okay. 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 All right. That's good. Okay, that's a good one. All right. So we pray and hope the results are going to be in your favor and everything would come out well. Um, okay, so uh, let's look forward to a good one. I think uh, I'd say that somehow, hmm, I'd say that I would kind of miss our classes, but it's all good. Maybe there would be another opportunity in future to do something else together. Probably not on the academic side, something different, I guess. But anyways, I'll be looking forward to get hearing what the results are. I guess you'll be able to share with me when they're out. And yeah, looking forward to that.
Yeah.
Okay. Yeah. So let me not keep you up too late. Okay. So um do have a good night rest and uh wish you the best in the exams tomorrow.
Thank you.
All right. All right. Take care. Bye.
Bye.